We're going to cover Chapter 1 in our... Now, I'm using the new book, okay? So the information in the new book and the old book is pretty much identical. So as I'm reading this, if you may have to take a minute to find where I'm reading. Mine starts on page 2, and it says History of Welding. Locate that. And then it says Chapter Objectives. And it lists 10 objectives that we're going to try to touch on here in this chapter. Let me go over them real quick. The first is you should be able to explain the history of metalworking and welding. When we're done, you should be able to explain the development of modern welding. You should be able to give details of the mission of welding in the industrial process. That's kind of abstract, isn't it? You should be able to describe the diverse welding processes. That's an important one. List the various welding occupations. There's a lot of different things that involve welding out there. Define welder qualification and characteristics. Super important. You can't be a qualified welder without being certified. Express the duties and responsibilities of a welder. Recognize welder safety and working conditions. Identify trade associations and what responsibility they have in the welding industry. And this one's, again, probably isn't too pertinent. Establish goals to keep you up to date in the field. Okay. So, I was asked if I'm going to teach to the test, but I don't know if you could define it as that, but I do have the test in front of me, and it just so happens that I put this test together myself. And the one from the old book came from a bank that the authors did, and I was never happy with that. So you guys are going to get the old test, but the questions are about the same as they are on the new test, only I've expanded it, made it a little more clear. So I'm going to touch on all the questions, and actually I'm going to hit all the high points, and as I'm going through here I'm going to say highlight this and put a bullet by that, and you'll know that's where I'm bringing the questions from. But in addition to that, I want to get all the important factors. Now I'm going to touch on more things than there's going to be questions, so be aware of that. And we're going to start on, in my book it's page 2, where it says Overview, Welding. We'll get to that picture in just a second. I'm reading from your book now. It says welding, and this is a definition. Anything in bold is a definition, and it's probably going to be on the test. Welding is the joining together of two pieces of metal by heating to a temperature high enough to cause softening or melting, with or without the application of pressure, and with or without the use of filler metal. Now that's a definition that's put out by the American Welding Society. They've got a big old book of definitions, and it's called Standard Terms and Definitions. And when you go through all of our classes, we're going to be using standard terms and definitions. All of these slang terms like overlap, not overlap, but cold rope, and there's a whole bunch of them that we'll come across. If I hear you using non-standard terms, slang, I'm going to correct you with the standard terms because you have to be able to communicate effectively to be in this business. Continuing, it says, any filler metal used has either a melting point approximately the same as the metals being joined, or a melting point that is below these metals but above 800 degrees Fahrenheit. So they put that figure in there for a reason. You're going to want to remember 800 degrees Fahrenheit. You're not doing welding if you're below 800 degrees Fahrenheit. Okay? Let's go over to the next page. History of metalworking. This is some of the background and how we got where we are. Again, I'm going to read from your book. Metalworking began when primitive people found that they could shape rocks by chipping them with other rocks. The first metal to be worked was probably pure copper because it is a soft, ductile metal that was widely available. Now, when I lived in Arizona for 4 years, and they have what's called native copper. You can actually just find chunks of copper laying on the ground, and it's soft, and they could pound it, and they could shape it, and the Anastasi, they made little tiny bells, copper bells out of it, for use in religious ceremonies. Ductile is in bold, and again, you want to know the definition of this. Ductile is a property of metal, and it means that the metal can be easily hammered, bent, or drawn into a new shape or form. So that's a bullet. Excavations in Egypt and in what is now the United States indicate the use of copper as early as 4000 BC and before 2000 BC respectively. More than 4,000 years ago, copper mines on the peninsula of Sinai and the island of Cyprus were worked. Welding began, here's another bullet, welding began more than 3,000 years ago. when hot or cold metals were hammered to obtain a forge weld. So the old blacksmith, when he would heat them in an oven or heat them in a fire and then throw them on the anvil and pound them with a hammer, he was doing forge welding. Okay. Some of the forged metals were bronze and iron, and these were mentioned in the Old Testament. It says archaeologists have determined that bronze was developed between 3000 and 2000 BC. Now bronze is a mixture of copper and tin. Pretty sure it's copper and tin. I might be wrong on that one, but I'm almost positive it is. And iron became known in Europe about 1000 BC, several thousands of years after copper. And it's funny, it was kind of war that developed this, that spurred the development of this. Way long ago, like 4000 BC, you guys remember the Iceman that they found in Europe a few years ago, and he had a solid copper axe, right? He came from the Copper Age. Well, they had copper swords in Egypt and stuff like that then. Well, some of the empires that replaced existing empires did so because they developed iron swords. Iron swords were stronger than copper swords, so they could defeat them in battle. So war really had a big driving effect on the development of metallurgy. Drop down, and it says the famous Damascus swords and daggers were made in Syria about 1300 BC. These were sought after because of their strength and toughness. Toughness is a metal property, okay? Their keen edge was likely capable of severing heavy iron spears or cutting the most delicate fabric floating in the air. The swords were made by forge welding iron bars of different degrees of hardness, drawing them down and repeating the process many times. And they call that folding. They'll fold the metal and beat it and fold it and beat it. Here's a bullet. The working of metals, copper, bronze, silver, gold, and iron, followed one another in the great ancient civilizations. By the time of the Roman Empire, the use of iron was common in Europe, the Near East, and the Far East. Here's another bullet. The Chinese developed the ability to make steel from wrought iron in AD 589. What's the difference between iron and steel? Anybody? Anybody know? Iron is a combination. Well, it's taken out of the ground as ferrite. It's melted in a smelter, and you can get it back to pure iron. But if you take just a tiny, tiny, tiny bit of carbon, way less than 1%, and mix it in with that iron, now you have steel. And what happens is when you put a little bit of that carbon in there, those molecules, they alloy with that, and they give it extra strength, extra ductility, and it was a huge step in the development of our modern age by improving the quality. Steel was better than iron. Just as iron was better than copper, steel was better than iron. So it was a huge development, and the Chinese were the first ones to do it. So now that is not in your book, but remember, it's the addition of carbon to iron to make steel. Okay, I have to flip the page here, and it says, by the 8th century, the Japanese manufactured steel by repeated bending and forging and controlled the amount of carbon in steel by the use of fluxes. They produced the famous samurai sword with a blade of excellent quality and superior workmanship. So here your book talks about the addition of carbon. Let's see, drop on down. You can read a little bit more about Eli Whitney and the Industrial Revolution. Then let's go to the early developments in welding. Here's a bullet. At the beginning of the 19th century, Edmund Davy discovered acetylene. Acetylene is a gas that was later used in oxyacetylene welding, heating, and cutting. Now, acetylene is actually mined in this book. I believe it's back on page 146 in our new book. Let me see. If you have any questions at any time that we're talking, just let me know. Here we go. Briefly on acetylene, I'm reading on page 146. It says, commercial acetylene is made from calcium carbide, which is commonly referred to as carbide. Carbide is a gray, stone-like substance that is the product of smelting coke and lime in an electric furnace. And then they dissolve that in water or what they call an acetylene generator, and they actually manufacture acetylene in that way. Acetylene has the greatest BTU production of any of the fuel gases that we use. So that's acetylene. So that was a bullet. Know what acetylene is. Drop down to the next paragraph where it says, the first documented instance of fusion welding, this is a bullet, was done by Auguste de Meritens in 1881. He welded lead battery plates together with a carbon electrode. Two of his pupils in Bernardos and I can never pronounce that name, Olszewski, saw the possibilities of this discovery and experimented with the arc powered by batteries that were charged with high voltage dominoes. After 4 years of work, they were issued a British patent. So the first welding took place from a bank of batteries, and it was a DC current. So if you might want to make a note in your off to the side someplace in your book that it was a DC current and it came from a bank of batteries. In my book, I have to move to the next column, and it says bare metal electrode welding was introduced in 1888 by a Russian. His discovery was first recognized in Western Europe in 1892. L. Coffin was one of the pioneers of the welding industry in the United States. Now, you're not going to have to remember these names, but remember the dates. Remember the dates of when the thing was developed. I'm not going to ask you any questions about the name of the discoverers. Okay. Drop down a little bit and it says, by the turn of the century, welding was a common method of repair. So that means as we were changing from the 1800s to the 1900s, welding was coming into its own. At this time, welding was given added impetus by the development of the first commercial oxyacetylene welding torch by two Frenchmen, Force and Picard. Oh, he was on Star Trek. Bare electrode welding became the prevalent electric arc welding method used in the United States until about 1920. And they used bare electrodes with an electric arc. Can you imagine if you took a stick of our TIG wire and put it in your stinger and tried to weld with it? Can you imagine what would happen? Well, that's what they were doing. Of course, they were using lower currents and lower voltages than we are. But I'd like to tell this story. It's not in your book. It's an anecdote. And remember it because you may have a question on it. What happened, one of the things that helped them move from bare electrodes to covered electrodes was they would leave some of these bare electrodes out in the weather and would develop a thin film of rust. And then they found that with that thin film of rust, it actually welded better. So they began experimenting with different coatings, and that was kind of the impetus to develop chiller metal electrodes. And then, of course, they wanted to change the mechanical properties of whatever they were welding, so they would begin adding alloying elements such as carbon and manganese, just all kinds of different things, vanadium, columbium, chromium to get stainless steel, and so forth. So anyway, remember that little story about leaving welding electrodes out in the weather. Okay. Let's see. In 1907, I'm in the middle of the next paragraph, Kleilberg, a Swedish engineer, received a patent covering the electrode coating process. So by 1907, they were some of them were doing coatings. The coating was thin and acted only as a stabilizer of the arc rather than as a purifier of the weld metal. See, today they'll put in scavengers and purifiers, deoxidizers, all kinds of things. We've come a long way to get the quality of welds that we have. But when they first started, they were just tickled to just be able to stick two pieces of steel together. Never mind all the porosity and everything. Drop down to the bottom of that paragraph, and it says, see Figure 1-2, Bernardos patented a process in 1908 that has come into popular use in the past few decades. This is the Electroslag process of welding thick metal plates in one pass. Now, I think I might have a slide of that in this presentation, which we'll do later. I'll get to it in just a minute. Let's get this thing off of here. As we get to that, I'll put up a slide of electroslag, but essentially what it is, it's a casting process. And they'll take copper shoes, and they'll start a weld here in the bottom, and they feed wire into it, and they use an electric arc to initiate the process, and then the slag that they put in there, the flux that they put in there becomes so hot through a chemical reaction that it melts all of that metal. And they do it in one pass because they could take and make a weld casting as big as this book, and they could build it up and up and up and up and up and up, and they could make it 5 feet tall if they wanted to. So it's a pretty neat process. It's not a manual process. The hard thing about that is setup time. It takes a long time to set it up. So electroslag. The thing you want to remember here, because we're early in this, just take that one paragraph. This is the electroslag process of welding thick plates in one pass. Okay, so that would be your key. That would be your bullet. Go to where it says at the end of World War I, and there'll be a question on this. Welding was widely accepted. Research on coated electrodes through the 1920s resulted in the electrode coatings and improved core wire. This significant development was the main reason for the rapid advancement of the stick welding process. This term has now been superseded by the term shielded metal arc welding, SMAW. Now you're liable to have a question on your test as to what does SMAW mean. It doesn't mean stick welding, it means shielded metal arc. Okay? And the reason it does, here's a picture of the shielded metal arc process, and I don't have my pointer. And if you can imagine your 6010 welding electrode is here. This is a cutaway view of it. Here's the solid metal. As the electricity passes through, it melts it, and you have metal droplets and slag being transferred. So it's shielded because as this is broken down by the heat, it creates a little gaseous shield that protects the liquid metal. So it's a shielded metal arc. Metal, because there's metal in the welding process. So that's where it gets its name. It's shielded by the shielding gas. You have a metal arc transfer, and you can see the shielding atmosphere, the weld pool, the depth of penetration, and so forth. So SMAW means shielded metal arc welding. Know that. It will be a question. The next topic says the development of modern welding. During the post-war design, welding machines changed very little. Since welding was first done with direct current, DC, from battery banks, it was only natural that as welding machines were developed, they would be DC machines, blah, blah, blah. So that's a bullet. Again, they started out as DC machines, but then they began research in the 1930s, bullet, 1930s, about alternating current, AC currents. Does everybody understand what the difference between DC and AC? You guys familiar with that? Boy, what a lively crew I've got here today. Let me show you real quick. Okay, if you go into the welding lab and you look at one of those old red-faced Lincolns that we have sitting there by that shear, it looks like this, and it's got a big handle here, a crank handle that you can change the settings on the amperage. And if you look at it, up here it say DC, and down here it says AC. And you look at the amperage numbers. And as you go along, the amperage numbers here for the AC will get higher. They call it, this is a 250 amp machine on the AC side, but it's only a 200 amp machine on the DC side. When electricity is moving here in the United States, electricity has a DC positive and a DC negative wave. Okay. Now I'm not much of an electrician, but I know this little bit about electricity. And here in the United States, remember that voltage is what puts the pressure behind the amperage and makes it move through the wire. So as it's moving, it's cycling like this, back and forth. It's jumping back and forth between AC and DC. That's alternating current. Okay, and if we were running on alternating current on those red faces that we have in there, you could get up to 250 amps. But when we're welding with DC, we send that same electricity through what's called a rectifier, and that'll be on a test, if not soon, if not in 1755, then in 1760. It sends it through a rectifier, which will take that, and it eliminates one half of it so that you have just DC positive, or you can switch it and go to DC negative just by switching your electrodes. Well, when we switch it, we lose some of that energy, and so on the DC side, we only have a maximum of 200 amps. And that's how it works. It cycles back and forth. And here in the United States, it's 60 cycles per second. In New Zealand, it's 45 cycles per second. I'm not quite sure what it is in Europe, but I think they're also on the New Zealand standard. So that's a little bit about electricity. And again, I try to give you guys and gals a little bit more than what's in your book, so that you have a full understanding of what we're discussing. And every little little side tangent that I get on, there may be a question in your book on that. So remember that. Okay, so we're still reading about AC, and it says World War II, this is a bullet, World War II spurred the development of inert gas welding, thus making it possible to produce welds of high purity and critical application. A patent was issued in 1932, Hobart and Devers, for the use of the electric arc within an inert gas atmosphere. The process was not well received by industry because of the high cost of argon and helium and the lack of suitable equipment, but that was industry. What they developed was the gas tungsten arc welding process. Now, you may hear it called heliarc. You may hear it called TIG, T-I-G. So here's a couple of more terms that you should be familiar with. So gas tungsten arc welding is also known, aka also known as TIG, which is tungsten inert gas, or it's also known as heliarc. Okay? It was developed by DuPont. These guys worked for DuPont. Hobart was one of the guys' names, and Devers was the other one. And that's still a proprietary name. Pretty sure it's Lindy and Hobart. Anyway, they own the rights to that name. So all these different names may be used to describe gas tungsten arc welding. So you may get a question on that. Okay? Drop to the next paragraph where it says, Russell Meredith, an engineer at Northrop Aircraft Company, was faced with the task of finding an improved means of welding aluminum and magnesium in the inert atmosphere. Because of a high burn-off rate, magnesium produced procedure was replaced by tungsten electrode, and a patent was first issued in 1942. Why? Because World War II. Airplanes. Yeah, that P-51 Mustang that crashed in Nevada, its seat was originally welded, with the gas tungsten arc welding processes, and that replaced bolting it in place. Because during the Second World War, when these guys turned over, and this is history, when they turned over, sometimes those bolts would break and the guy would fall against the canopy, lose control, and die. So they developed this. It was safer, stronger, and it worked. So later in 1942, remember that date, the Lindy Company obtained a license to develop the gas tungsten arc welding TIG process, also known as heliarc, blah, blah, blah. Okay? And then they have a picture of an aluminum weld there at the bottom. So that's a little bit of that history. In my book, I have to switch the page, but I'm reading now from the paragraph that begins in 1948. The U.S. Patent Office issued a patent for the gas metal arc welding process. Gas metal arc welding. Okay, so that was developed in 1948. Gas metal arc. Okay, they also call it GMAW. See, we got GMAW and we have metal inert gas and metal active gas. So when we talk about gas metal arc, I think I have a picture of that. Let me see. Nope. Okay. In gas metal arc, you've got your gun, your nozzle here, and the wire's coming out, and it kind of pinches off, depending on the transfer mode that you're using. And so it too creates a transfer. It actually short circuits against the metal, and it pinches off, and it's shielded by a shielding gas, but it's an arc welding process, so that's where it gets its name, gas shielded metal arc welding. And it also has what they call MIG for gas, metal inert gas. There's lots of gases. There's inert gases and there are reactive gases. And then they have MAG, which would be an active gas or reactive gas. The most common is the kind with inert. So when you hear somebody say MIG, they commonly refer to it as MIG. On your tests, and the proper way to talk about it is as gas metal arc welding. So you may be asked a question relating to that. Understand that MIG is an old term. Gas metal arc welding is the proper term. So read that. And the other important, there's going to be a question on that. And the other important thing to take from that paragraph is towards the bottom of it, where it says the use of gas metal arc has increased very rapidly. It is now used in virtually all industries. A gas metal arc or similar process is responsible for over 70% of all the welds performed today. You would think that shielded metal arc would be, but it's not. It's those little wire guns do 70% of the welding in the world. Okay? All right, let's see. Next, let's go to all those bulleted items where it talks about some other processes. We have the arc welding process, atomic hydrogen welding, electroslag. This is not going to let me go, is it? It keeps wanting, that computer keeps wanting me to do something. So electroslag welding, this is what I talked about before. It's a little hard to see, but right down here, this is where they're making their casting. These are water hoses, and these are copper shoes. One of the things they have to do with electroslag welding is keep it cool because it gets so hot. And this is why it's a casting process. Here's a Hobart machine. Those of you that go and eventually take welding inspection technology will get into this pretty thoroughly. But just, again, from your book, just take it out that this wire being fed down in here can allow them to weld from the bottom to the top in a single pass. So that's the important thing about electroslag. Well, here's kind of a diagram of it. So you can see it. Here's the copper shielding, the water lines, and the metal being made. And you see there. And the other thing is it has to weld from the bottom to the top. There's no out of position welding with that. Plasma arc welding. This is an awful lot like gas tungsten arc welding. They have a couple of kinds. They have what's called a transferred arc and a non-transferred arc. This here is a transferred arc. And again, when we get into welding inspection, I'll go over this much more thoroughly. One of the things you got to remember about all of these little welding processes. First of all, there's over 90 of them, which is going to be a question on the test. And you want to remember the abbreviations. This would be PAW, plasma arc welding. Okay, so you're going to want to remember those. Stud welding. Stud welding. You can see this guy's using a stud gun. That'll be a question on a test. A stud gun to attach bolts or hooks or eyes or pins or whatever to what's called a planar surface. So right here you can see he's attaching stuff to these metal plates right here. And so he's pushing down on the stud gun, pulling the trigger. There's a brief flash, making his weld, and he's moving on to the next one. I've used one of those things. But again, I'm not going to go into it now. It's abbreviated SW. Okay, remember these abbreviations. Submerged arc welding. Submerged arc welding. This guy is welding a pressure vessel, and it's called submerged arc because the wire is fed in through here, and this hopper is full of flux. Imagine if we took all the flux off of these welding rods, crumbled it up, and put it in that hopper. So the hopper, the flux, the coating is fed separately, and it completely buries the arc. So he's welding right now, but he's not using a welding hood because the arc is submerged under that blanket of flux. That's where it gets its name, SAW. We have one in there. Eventually, if you guys go far enough, I'll train you on that. And again, there's people taking that class all the time, so you could watch somebody doing that while you're in there. Electron beam welding, I had an opportunity to observe some of this at American Airlines in Tulsa. They do it in a vacuum chamber. That would be something that you want to make a note of. Electron beam welding, EBW, is done in a vacuum chamber. So they could do it out in outer space without any problem because there's a vacuum out there. So EBW, electron beam welding. They use it in the aerospace industry. It makes really deep penetration, thin welds, pinpoint accuracy, and they use it on turbine blades on an airplane motor, for example. Laser beam welding. A laser beam that doesn't have to be done in a vacuum, but they can send that beam and reflect it off of mirrors and go around corners and everything, and it's really kind of neat to see training videos on it, but I've never got to see it in person. It's very similar to electron beam welding in the quality of the welds that they do, and they also use it in aerospace, so that would be our spacecraft and our airplanes. Then, let's see, I think I skipped one, maybe not. Okay. So we're stopping there, and then right below those bulleted items it says today there are over 90 welding processes in use. Okay, 90 welding processes in use, and that's not counting the some of the others like stir welding. Look back at that bulleted item. 1, 2, 3, 4, 5, 6 up between laser welding, just above laser welding, friction stir welding, and friction welding. Now, a machinist came up with this. Right? He's machining a part, and he's got a couple of parts, and he butts them together, and he's going to try to mill them down, and he finds out that, my God, look at that, they're hooked together. What happened? And from those simple little discoveries, one of those serendipitous revelations, they developed stir welding, and they started with aluminum. They're still doing it with aluminum, and they can butt material together. And they use a drill bit or a spinning head with their bits, and they can go through there and they can actually get that metal so hot just by rotating equipment that it'll weld itself together. And they are developing, they've got some now that will do it to steel, but it started out on aluminum. So stir welding, I'm talking about stir welding for a reason, so remember stir welding. Okay, then finally the last subject on this topic are where they talk about the organizations that take care of weld certification. And it says, currently 5 welding associations provide guidance and standards related to the welding industry. Okay? The first one says the American National Standards Institute. The American National Standards Institute doesn't write welding codes, but it approves welding codes. That's an important distinction. It says, okay, your welding code is all right. We approve of it. But they don't write them themselves. The ones that write them, and the most important ones you're going to be concerned with, are the American Petroleum Institute, API, the American Society of Mechanical Engineers, ASME, the American Welding Society, and the American Bureau of Shipping. And those are the important ones. We're not going to deal with the shipping one, but in our area, those other 3 are the very most important ones, and you will get questions on that. So these are pictures of some of the code books. Here are some of the code books. This is ASME Section 9. If you take a weld qualification test in our area for piping, power piping, or say SF phosphates down south of town, or the power plant, you're going to be testing to ASME Section 9. Okay, and as we go through these things, you're going to learn how to recognize what is good and what is not good, and everything that Jeff and I teach you is in accordance with what's in these code books. Okay, so that's ASME, the American Society of Mechanical Engineers. This is the main AWS code book. This is the AWS D1.1 Structural Welding Code. This is the structural weld. Pretty big, pretty thick. But this test right here, if I were to give it to you, comes out of this code book. If you pass this test in accordance with this code, you're a certified welder. Okay? And then we have this book. Look how thin that is. That is the 1104 code. Any of my students that take my welding inspection class, if they want to go to be certified welding inspectors, they give you the choice of which code you would like to take your test out of. And I always recommend this one because it's so small and easy to get around in. This is API. Those guys that you see driving around with welding machines on the backs of their trucks, most of the welds they make are in accordance with this little code book right here. So, API, AWS, and ASME. Remember those 3 organizations. Okay, welding as an occupation. Okay, let me read from your book. It says, a student needs to learn all phases of the trade. Welding, reading, drawings, math, and computer knowledge will secure a successful career. Many qualified welders are certified by the AWS, ASME, and API codes. The tests are difficult and require many hours of practice. To weld, you need talent. You need ability. And even if you have varying degrees of talent and ability, we're going to help you to develop that talent and ability to the max. Okay? Let's see. This would be a fillet weld test. This is a fillet weld. This also comes out of D11, so that would be one of the tests that you guys would be taking. This would be a groove plate test, also out of D11. I'm not sure what that is doing in there, but that is resistance welding. This is a resistance weld. What they do is these are electrodes, copper electrodes, or brass. I forget exactly what they're made out of. And they pass electricity between them going through this thin metal here. And it creates a spot weld. So those are spot welds. It's abbreviated RW. Looking in your book, it says welding is gender friendly. That's a bullet because although I won't give you a question on that, you may get a question on that. Let's see. Continuing reading from there, keep in mind that the field of welding can offer you prestige and security. It can offer you a future of continuous employment with steady advancement at wages that are equal to other skilled trades and are better than average. It can offer you employment in practically any industry you choose and travel to all parts of the world. It is an expanding industry and your chances of advancement are excellent. That's why a lot of our programs here on campus require you to have some welding. Industrial welding applications. Welding is not a simple operation. The more than 90 different welding processes are divided into 3 basic types: arc, gas, and resistance. A number of other types such as induction, forge, thermite, flow welding, and brazing are used in a somewhat lesser extent. And here's why I put this in here for resistance welding. This is a bullet on resistance welding. Resistance welding includes spot welding, seam welding, flash welding, projection welding, and other similar processes that are performed on machines. You will probably get a question out of that paragraph. Spot welding, out of all of those, spot welding is probably the most common one, and they use that on, again, heavily in the aerospace industry, but a lot of industries will use that. Flip the page. Well, pardon me, in my book I have to flip the page. I'm going to the last paragraph on that topic, and it says gas welders may specialize in oxyacetylene or gas tungsten arc welding processes. Some welders are skilled in all of the processes. You should acquire competence in shielded metal arc welding, gas tungsten arc welding, and gas metal arc welding processes on both plate and pipe. If you're going to be fully qualified, they want you to learn all of those. We offer the 5 main welding processes and the 3 main cutting processes in our classes. Qualification of personnel. Everything has to be inspected. That's a bullet. Read that. Everything has to be inspected. You're going to get some questions on that. Certifications are issued according to the kind of gauge or metal and the specific welding process that is used, the technique that is used. Some welders hold several different certifications, but everything has to be inspected and tested. So there's several different ways of testing. One of them, again, if you get into my inspection class, I'll take you over this. This is called a yoke. Real briefly, I'm trying to hurry up here. This is called a yoke. You pull this button here, and it passes an electrical current through here, and it can magnetize a piece of steel. We sprinkle some powder in there, and that powder is drawn to any cracks or anything that's in the steel. This is abbreviated MT for magnetic particle testing. MT. It's not in your book. Write it down. You may get a question on it. Next to visual inspection, the most common type of inspection is PT. This is a PT kit. In here I have some cans that I can spray onto a weld, and by using a dye on this piece right here, I sprayed some dye on there, and that dye can be drawn out of any bad spots. And by using that dye, this dye penetrant testing is what it's called. It's abbreviated PT. I can see things that I can't see with my naked eye. So PT is another commonly used type of testing method. But out of those testing methods, there's still several other, like X-ray and all of that. The most common one is this one, visual inspection. looking at something and being able to tell what's wrong with it. It's the cheapest, it's the most efficient, and when I go on a project, if I don't do anything else, I look at every weld. And you are your own best inspector, so understand that. Write down these abbreviations and know that VT, visual inspection, is the most economical, efficient, fastest, cheapest, VT. Okay. Let's see. Continuing. Highlight where it says welders must also be able to cut metals with the oxyacetylene cutting torch and with the various cutting procedures involving the plasma arc cutting machine. This is a bullet. Flame cutting is often the only practical method for cutting parts or repairing steel plate and pipe. Plasma arc cutting is used to cut all types of metals. Proper use of an electric or pneumatic grinder will save many hours in the welding process. So in addition, this is an x-ray tube. We have an x-ray machine in our lab that you're free to look at anytime you want. This is the UT process. This is oxy-fuel cutting, most common. If you're going to be a welder, you got to know how to use an oxyacetylene cutting torch, which is why I insist on everyone taking Weld 1715. This is a plasma arc cutting table. It's actually a water table. The arc is suppressed underneath the water to keep it quiet, but we have a manual hand-operated one that you'll learn in 1760. This is air carbon arc, and this is a manual handheld carbon arc. This is another one of the processes. So there are three primary cutting processes, and I want you to remember them. They are oxyacetylene cutting, plasma arc cutting, and carbon air cutting. Okay? Those are the three main ones. So remember those. And then read over all of the different things that you can do as a welder. They're saying in the book that you require a high school education. You really don't, but they want you to. And they believe that some of these require college. You could be a CWI, a certified welding inspector like I am, with an 8th grade education. They value experience more than education. Let's see then. This is the plasma. This is the air arc, and that's all my slides. So we're almost done. Safety and working conditions. Highlight where it says job hazards may include fire danger, burns, sunburn that you get from the welding arc, noxious fumes from materials vaporized at high temperatures, eye strain, welder flash, and electric shock. These hazards can be minimized or eliminated by the use of proper protective clothing, safety shoes, PPEs, they're abbreviated PPEs, personal protective equipment, face shields, goggles, so forth. When performing jobs, welders always take precautionary measures for their own safety and the safety of others. That's a bullet. When performing welding jobs, you're always going to take precautionary measures for your own safety and the safety of others. And then one last thing I want you to put in your book, write it off to the side someplace. Even clear safety glasses will knock out 75% of the harmful ultraviolet rays from reaching your eyes. Clear safety glasses, which is why one reason we insist you wear your glasses at all times in the welding lab. Even these will stop 75% of UV rays from reaching your eyes. Okay? Okay, that covers the book. Now, your test is going to consist of 30 to 35 questions. Some of the questions are going to come from the back of the book. There are review questions there. I suggest you read those review questions, look up the answers, because they are going to be identical to the ones in the back of the book. I don't know how many I'll take. I might take 5, I might take 6, I might take 8, but some of the questions on your test will be from the book. Any questions on Chapter 1?